Hi, my name is Meredith Leich, and I am a Chicago-based visual artist who works in video and 3D animation.
Hi, I'm Andrew Malone. I'm a climate scientist studying tropical glaciers and the response to past, present, and future climate change. We started collaborating as graduate students in Chicago through a project funded by our institutions, the School of the Art Institute of Chicago and the University of Chicago. Our project is titled Scaling Quelccaya, and that's what we'll be talking about today for this conference.
And we'll talk both about the content of our project, but also about what it's like to build a scientist-artist collaboration and the potential for conveying scientific information in a more imaginative, psychologically astute manner by inviting viewers to learn and consider without inducing fear. To begin, I just want to talk a little bit about the genesis of our project. I was concerned about climate change before I met Andrew, but even though I read the news and was an interested observer, I had very little knowledge of the science surrounding climate change, and thus a vague idea of how we were actually getting our information about how the world is changing. So when I reached out to Andrew, I was reaching out with a fairly blank slate. Our collaboration is really based on taking Andrew's research and attempting to visualize it and transform the information in such a way that it can reach people more directly than looking at a graph or table with a series of numbers.
My research on tropical glaciers, which is any glacier between the tropics of Cancer and Capricorn, grew out of a general desire to understand present climate change and its human impacts. I am motivated in my science by a charge to gain insights that will aid humanity in addressing the upcoming challenges associated with climate change. Meredith and I gravitated towards each other and ultimately collaborated, I believe in part, around the question of how can we creatively and effectively convey this much-needed information about climate change. Early in our collaboration, we decided to focus our energies on one of my case study tropical glaciers, the Quelccaya ice cap in Peru.
The Quelccaya ice cap is the world's largest tropical ice mass. It's located here. It's that sort of large mass of white, roughly in the middle of your scene, and it's about 100 miles southeast of Machu Picchu. It's an ice cap sitting on top of a relatively broad plateau in a pretty rough landscape. So we're looking here from the west at the east. So the ice sort of interacts with the surrounding landscape through these series of outlet glaciers. And one of these outlet glaciers on the western side, and the ice cap in general, sort of gained some broader notoriety in 2013 when the New York Times ran an article about it and the sort of changes observed. So here we're looking at the Quelccaya outlet glacier in 1978 on the left and 2011 on the right. And over the course of these about 33 years, the ice cap has retreated about 1.5 kilometers. So I think the question that we've been asking is, what is 1.5 kilometers in sort of a visceral sense?
Just to sort of start to get our bearings, one of the first things that we did was to map Quelccaya on top of Chicago. One of the things that I've noticed in taking climate change media is that people are always comparing glaciers to Manhattan. They're like, a chunk the size of Manhattan fell off. It's like, okay, let's put the glacier on Chicago. So this is Quelccaya just superimposed on top of Chicago, and you can see here, their little Chicago insignia tells you where we are at this very moment. And then the black square is SAIC in downtown Chicago. So it's about halfway, a little more than halfway up Quelccaya, just to give you a sense of how big this ice mass is. And even using this image tool, which is just Google Maps, I mean, everyone has used this many times, raises the question of how do we have even these images?
Since July 23, 1972, with the launch of the Earth Resources Technology Satellite, the U.S. has managed a remote sensing program for purely civilian purposes. The program, now known as the Landsat mission, continues today. The 8th iteration satellite, Landsat 8, launched on February 11, 2013. Landsat 9 is projected to launch in 2020. The Landsat sensors do not just take snapshots of the Earth's surface, they measure the amount of light reaching them in specific wavelengths. This light is sunlight that has passed through the atmosphere, reflected off the surface, and returned back through the atmosphere to the satellite. The sensors measure the intensity of the light in the visible range around the wavelengths of red light, green light, and blue light, as well as in the ultraviolet and infrared ranges. By combining different combinations of measurements, color scenes can be constructed from these grayscale images. Using the images for red, green, and blue light produces what is called a real color image, which is essentially what we'd see if we were looking down from the satellite. Shown here is a real color image from Landsat 8, taken on September 16, 2016. Varying types of land cover are more or less effective at reflecting light at a specific wavelength, and by knowing these spectral properties of the land surface, different combinations of measurements can be used to produce what are called false color images. In the false color image shown here, the water, ice, and snow in blues really pops out from the surrounding landscape in red and vegetation in green. Even within the blues, spectral differences allow the glacier, snow, and ice in lighter blues to be easily distinguished from the melt ponds and lakes in darker blue.
So what you're seeing here is about 15 months worth of data of Quelccaya and Chicago, and the images aren't taken simultaneously. They're about 4 days apart because it takes that long for the satellite to make its trajectory around the planet.
These spectral differences allow automated and semi-automated processes for isolating glaciers. With the Landsat mission, Meredith and I were able to map in 2D the Quelccaya ice gap, but we wanted a richer spatial story, which required us to go to an additional remote sensing technology.
In 2000, they flew the Space Shuttle Endeavour upside down, and with radar were able to construct a height map of the surface. This was called the Shuttle Radar Topography Mission, or SRTM.
And this is what an output would look like. It's called the digital elevation model. It's just a grayscale image where whites are high and blacks are low, but high here is over 18,000 feet, and lows here are about 15,000 feet, so very high.
And just by chance or by fate, the same time that Andrew and I were having these early conversations, I was working in Marlena Novik's class, and we discovered that there was a method to bring those DEMs into the gaming program Unity and read the information that is encoded within the DEM back into 3 dimensions. So not a sculptural 3 dimension, but a virtual 3 dimension. So what you see there on the bottom is a virtual terrain from an early test of Quelccaya. So it's actually pretty wrong, but that was our first prototype. And so then taking that from Unity and into the animation program Maya and combining it with the city of Chicago, we were starting to be able to bring Chicago and Quelccaya into a more elaborate scale than that first Google Maps composition. So here you see Chicago floating over Quelccaya, and here's another view. And then just starting to play around with ways of creating comparisons that we might understand as something that we've walked in our bodies and taken public transportation through and lived in. So this is a meter by meter comparison. So as this much of Quelccaya is disappearing, the equivalent amount of Chicago is.
And sort of as we were moving along in our collaboration, we wanted to come back to that original question about glacier change and how can we really feel climate change in the tropics when we're sitting here in Chicago. So Landsat not only gives us sort of a static picture, but we can also look at change. So this here in the darker blue is the 1985 ice extent, and the lighter blue was 2015. Even though Landsat's a 40-plus year mission, really the last 30-plus years, we've been able to get this sort of spatial and spectral resolution to be able to do the type of analyses needed to make these types of images. But we at least can see the change over 30 years. Here, in just the red is just the difference between the two. But we want to sort of know something about height changes and the sort of amount of ice. So we used some of the data from Landsat. We just outputted that into a spreadsheet, and then using some mathematical equations in the glaciology community, we could translate that into a volume of ice. And then if we asked, what if we took all of that ice and placed it into our model of Chicago, how high would that be? So
Placed it as snow.
as snow, yes. So the answer to that question would depend on the types of snow, like really fluffy dry snow, that stuff that's great to ski in. We're talking like higher than Sears Willis Tower, but perhaps maybe a more representative amount would be like 600 feet.
Of course, it's not to say that there's a direct link between what happens in Quelccaya and in Chicago. There's not. But working with the idea of these being two cold climates, both with snow, one of which we're very familiar with and one of which we're not, we're asking if we can translate what's happening far away to what's happening here. To consider another example, I'll return to the first image of the Quelccaya retreat that Andrew showed us of 1.5 kilometers. What would that distance look like within Chicago? It's about the distance between the Willis Sears Tower and the Tribune Tower, so you can see that about that distance of Chicago would have melted. To extend this further, we were thinking about how not just to use Chicago as a measuring stick, but to merge these realities. Not that the loop will ever be trundling along the surface of Quelccaya, but to ask the question, what does it mean to be thinking about a glacier in Peru while we're living in Chicago? We live in a world that's so collapsed by technology, email, phone conversations, Skype. We're constantly interfacing with places that aren't here. And so even though our physical reality remains divided, our mental and emotional experience of the world is very merged. We were thinking about bringing these elements into a single space as a representation of how our minds work, as well as trying to create a more imaginative way of looking at climate change. So I would suggest that even beyond our personal project and continuing to work on scaling Quelccaya, there's potential here for artists to be working with scientists more and drawing on the really rich knowledge and history of creating visually compelling materials that speak to the human experience and using that to convey information, scientific information that we've really only had access to for a fairly short period of time. So it's really something new and very rich artistic materials, even though it may involve a kind of shift of values within the artistic community.
Yeah, and with this collaboration with Meredith, I've really sort of gotten to reassess my relationship with the Quelccaya ice cap. I've spent a lot of time working in a very quantitative sense, being able to share what I've learned with Meredith and sort of be stimulated by her questions has really helped me reshape and sort of think about my relationship to this ice cap, this location that I've been studying for 4 or 5 years at this point, through a whole new lens, as well as using some new technologies, thinking about using 3D animation as a way to tell my stories. We often use a lot of visuals in science, but this has been sort of a new avenue for me. I think we in the climate community have had challenges in ways to convey our information in a way to the public that's sort of accessible and also interesting to them, and maybe a way to make them feel motivated.
Andrew brings up about the various technologies that we use, I think is really significant because we found that the technologies that we were using are actually very related in many instances, trying to take images of the world and then recreate models, even though we were doing it in different ways. It's working with visual representations of a much larger terrain than we've been able to measure previously. And so there's a kind of natural fusion of the technologies that we're using. And we hope in this way we can take advantage of some of the benefits of the developments in science and technology that we've created to try to keep up with the world as it changes. So thank you very much for listening to our talk, and we look forward to your feedback.